So, sorry, I have to introduce the next speaker, which is, what's his name again? Oh yeah, it's Flavio Dell'Acqua, and he'll be talking about, well, moving from DTI towards, you know, other models. Okay. Thank you.
Thanks, Alex. Okay. Okay, yeah, my talk will be exactly moving from DTI to more advanced method like HARDI, and just before then moving to the microstructure with the next speaker. So as we've seen, let's see if it's working, yes. With DTI we can do many things, and essentially with DTI we have the tensor is a nice biophysical model that describes the displacement of water molecule in 3D. And we can do everything essentially with just three numbers, the three eigenvalues. So in fact, if we look at the lambda 1, 2, and 3, essentially they are nothing else than the sides of the axis of the ellipsoid. So we can have axial diffusivity, axial anisotropy, we can have isotropy in the case when all the eigenvalues are the same, or also we can have more complicated cases like, for example, when we have too high eigenvalues, like in the case here in the middle, when we have axial planar anisotropy, sorry. And this is good because, in a way, with just three numbers, we can describe a lot of complex diffusion configuration. But at the same time, this is also an oversimplified description, because what is not included in this number essentially is lost. So even if we have crossing or more complex information in our data, as soon as we fit the tensor, we just put everything in three numbers in terms of shape. Now you also have three eigenvectors about direction, but the shape of diffusion tensor is only given by three numbers. And we can see this problem as soon as we start to look at more complicated structure. So, for example, if in the case of a single fiber, you see the displacement is okay for the displacement is correctly described by the tensor. But when, sorry, I'm just a little bit kind of, okay, much better now. When you look at a single fiber, the displacement is correctly described by tensor, but as soon as we have more complicated structure, for example, crossing fiber, we start to see that the tensor is not only providing just an average shape, an average profile, but actually is giving something, tell us something's wrong. So let's have a look at this picture here. So now that the shape of the tensor is actually not pointing in the right direction, so the maximum diffusivity is actually wrong. And the same thing is when we look at, for example, at the other case when we have a planar diffusivity. So we can see this then when we do tractography. For example, if we want to do tractography of the corpus callosum, we put a seed in the mid-sagittal plane of the corpus callosum. What we see is usually only the most medial part of the corpus callosum. We don't see the lateral projection of the corpus callosum. Now, borrowing a little bit improperly some terminology from statistics, which sometimes people say we have some false negative reconstruction because actually we are not able to see something that anatomically we know is there. We know the corpus callosum is connecting the whole left hemisphere with the right hemisphere and vice versa. At the same time, we have also some error. We can, if we look on the left side, we can see that we have what's called false positive. Sometimes, because again, all the tensor essentially is average information from different fibers. We have this kind of artifact, for example, here. Let's have a look at this false positive. This we can see the body of corpus callosum and then go inside the internal capsule. We know this is anatomically inconsistent, so there are no direct connection between the internal capsule and the corpus callosum. And this is because the tensor, in a way, is averaging together the corticospinal tract and a bit of the corpus callosum. But the problem are also when we look at on maps. For example, if you look now in this picture here, you see this kind of dark region. And this is not a lesion, this is a healthy subject. And when we see this, it's because, it's not because there are less myelinization, there is less anisotropy, but simply because we have a lot of crossing, and the average of different trajectory, we have a lot of this kind of cigar shape or high anisotropy tensor that together, the average together essentially end up to be like a sphere. So the average is a low anisotropy, but each individual fiber is actually with high anisotropy. So we need to move forward, but before actually start to look at the new methods, the solution for this problem, I want to ask you a question. Do we really need advanced methods? That's what actually was a question that someone asked me a few years ago, because when I was presenting one of the first posters on spherical deconvolution and advanced method, someone came to me and said, well, the work you're doing is interesting, but actually there are not that many crossing in the brain. Well, Now, well, I have the answer for that. Now, there are different publications. Now, we can clearly say that between 70 and 90% of voxel in the brain show crossing. So, and probably even more, because this is actually the crossing we can resolve now with our technique. But if we look more in detail, probably we can see even more than that. And this is a small atlas we made, and we call NUFO, a number of fiber orientation maps, and actually show how the crossing are distributed across the brain. As you can see, clearly, the crossing is almost everywhere in the brain, except the body of corpus callosum, makes sense, and also these two spots here, they're actually the core of the corticospinal tract. But everywhere else, essentially, we always have crossing. Always, we have mostly two crossing, and now if you remember the dark region we were seeing before in FA, is a region actually not of two crossing, but a region of three crossing, and that makes sense, because in this region we have the corpus callosum, fiber corpus callosum, the corticospinal tract, and all the associative fibers, for example, as SLF, arcuate fasciculus. So in the same region now we have three major bundles crossing together. And there it is, there you can see here, you see this kind of line. This is kind of a standard pattern. Okay, so yeah, we definitely need something better, something more to process our data. And, sorry, got the Mac one. And it's not only a problem of crossing, there's also a problem of kissing. This kind of a romantic name, but it's not that easy problem, because actually this is a problem we haven't solved yet. And just to explain very briefly, the question is, how can we, now if you look at this picture, it's easy to distinguish between a kissing and a crossing. And actually, when I talk about kissing, I'm not only talking about the kissing inside the same voxel, it's going to be something also in bigger scale, across different huge tracts. And if you look at this picture, the color is easy to discriminate, but with diffusion imaging, actually, this is what we have. So there is no contrast, there is no color to separate. The signal is exactly the same between a crossing and a kissing. So unless we use additional information, for example, using neighbor voxel or a priori information, it's quite difficult to discriminate between kissing and crossing. So even with advanced method, we have to be careful when we interpret tractography result, because we still some situation not being resolved. So how can we go beyond DTI then? Okay, so the first thing I want to explain today is actually tell you what is HARDI, because it's essentially is the base of all the advanced method we are using today. HARDI is nothing else, means high angle resolution diffusion imaging, and it's not the methods per se, but actually is a philosophy of how we acquire data. And the idea is, okay, if this is one biological system, so one fiber, then we can have a displacement. Now, instead of just measuring the right number of direction just to fit a tensor, what we want to do is to sample along a sphere. So we want to try to capture all the angular information we had available from the data. And then we want to generate actually this kind of profile, this kind of donuts. Unfortunately, I forgot to buy donuts to actually give you an example today, but this could be seen as a donuts of a beagle as well. And as you can see, the meaning of this shape essentially is actually it's quite difficult now from here to try to read now. But you see, if this is the direction of the fiber, the maximum amplitude of the signal is actually on the radial component, while on the long direction of the fiber you have no signal. So that's why we have this kind of symmetric shape. Now, if you have a single fiber, it's not really useful. It's not really, do we see anything new? But the things get more interesting when we start to have crossing. In fact, as you see now, there is more, the shape of this kind of profile is getting more and more complex. And now, from using this profile, we can have a new way of actually investigating and try to extract this cross information. And clearly, if you know now you're going to feed the tensor on this signal, you probably get, again, 3 numbers, but again, you're not going to solve any crossing. So the first method, the first approach historically we used to resolve crossing were actually multi-tensor method. And the idea is very simple. If one tensor is good for one fiber, let's use 2 tensors to solve 2 fiber crossing. And it's working okay, but there are some limitations we have to take into account. For example, we need to remember that there are some model selection issues. In fact, the first thing is you need, most of the first method actually requiring to know a priori how many fibers, how many compartments you want to fit. So that was kind of model selection issue at the beginning. Then also, if we want to complicate a little bit more the model form, instead of 2 fibers, you want to have 3 or more, the problem mathematically became not is completely solvable, because sometimes you have multiple configurations that give you the same signal. At the same time, well, you have to think about that the brain is not made only of discrete number of fiber orientation. It could also be organized like in a fanning structure. So you have a kind of distribution more than a discrete organization of fibers. So we can do something anyway, because, for example, if you introduce some kind of constraint, so assuming that the tensor is just axial symmetric, or we can impose some kind of information about diffusivity, then we can enforce some kind of information. Then in this case, we can build up and get better result. And probably the most known technique is probably the ball and stick model from Oxford group. And the idea is very simple. So we try to divide the isotropic component of the signal, so the diffusivity, and decompose that with the anisotropic component. In fact, for example, if we model all the anisotropy like a totally anisotropic tensor like lambda 0, 0, so this is essentially one stick and one sphere to describe to fit for the mean diffusivity. Now, with this model, we can actually expand to multiple sticks, and now you can clearly see that from one fiber to two fiber model, we can actually improve and identify new tracks, because now this, for example, this is the SLF1 is crossing with many fibers, for example, corpus callosum as well, and the corticospinal tract. Now, you need crossing fiber method to see SLF fibers, for example. Normally, with DTI, it's quite difficult to see this track. But probably the most known, I mean, the kind of what is getting now, becoming the standard to resolve crossing and tractography actually is now to use this kind of data type, this kind of structure is called orientation distribution function, or ODF. And there are different families. So I'm not going to explain all the possible models because I'm never going to finish in time today. But I'm just going to give you kind of a very brief definition of what are the two main families. One family is called diffusion ODF, and actually is the family of DSI, cubal imaging, DOT, and also GQI, and other similar methods. And the idea of this kind of ODF is that what we are trying to obtain is kind of a three-dimensional profile, this kind of multi-lobe shape, where each lobe actually is telling us the direction of the fiber, and also the amplitude somehow is telling us something about how much is in kind of the relative proportion of fiber in that direction. So without assuming anything about the number of fiber, their direction or distribution, just getting, we have methods that now can just provide this kind of shape for each voxel. And in the case of diffusion ODF, the idea is we want to obtain something that is directly related to the diffusion propagator. So I'm coming back in a second, explain more in detail what we mean for diffusion propagator, but the idea is we want to kind of capture the information on water molecule displacement and reconstruct this kind of diffusion ODF. That is nothing else than kind of the radial information, the probability of diffusion in different direction. On the opposite, we have the fiber ODF. The fiber ODF are not directly related to the diffusion displacement of water molecule, but directly try to use a model to infer the underlying orientation of fibers, and in this case, for example, and the typical methods, and the most common method is the spherical deconvolution. So given a fiber response, so if we take our own donuts as a model for fiber, and we want to see how this donut is fitting in our HARDI signal. So if we have this model, what we get as an output is the fiber orientation function. Okay, so just to stress on this point, because I think it's very important, diffusion ODF essentially are profile that directly related to displacement of water molecule. So we can have different kind of technique, but all of them, what they're trying to do, trying to kind of get information about this displacement of water molecule. On the contrary, when you look at fiber ODF, we are not interested in displacement of water molecule, but we are interested in the underlying orientation of the fiber. And this is what we really want if we want to do tractography, because we want the fiber orientation. We are not really interested in how the water molecule displays, okay? Although we have to be fair that the two things are clearly related. Okay, now, this was kind of a summary. Now, let's have a look in specific what we mean for DSI. What is the propagator? Well, the DSI is probably the most famous technique in terms of model-independent approach, and is based on a very nice relation that, given the diffusion signal acquired in a particular way, we can actually immediately obtain the diffusion propagator by using a simple three-dimensional Fourier transform. So in order to get this transform, we need to collect the data not properly as an HARDI acquisition, not as a single shell or acquired data in many direction, but with a particular acquisition based on essentially we need to acquire multiple b-value, multiple q-value along different axes, x, y, and z, in order to create a kind of three-dimensional Cartesian grid. If we collect this data in a proper way, we can just do a Fourier transform, and immediately with that, we get, for each voxel, a structure like that. So in each voxel now we have the probability of displacement water molecule. So this is kind of a three-dimensional information inside each voxel. Now, if we want to obtain now the ODF, and then do tractography out of it, what we need to do is simply do an integral, for a radial integral in every direction, and we calculate the total probability of displacement in every direction. And we get this kind of shape, the orientation, the diffusion, it is this distribution function. This method is very interesting because it's completely model independent. So it's essentially a transformation of the signal. So we don't have to impose any hypothesis. However, to get this working, we need we need a lot of time, because as you can see here, to get that we require about 500, 200 volumes, so it's a kind of time-consuming acquisition. And also to get a nice contrast to resolve nicely the crossing, we need also a high b-value. Now, also another thing that I haven't put in these slides, also we need to also consider, is that even if here we have a lot of volumes, we are talking about 500 volume, but if we divide 500 volume on the three axes, we have about 11, 11, 11, and our more practical acquisition, sometimes we have only something like 200 volume. That means 7, 7, 7. So, and if you try to do Fourier transform with 7 points, you can clearly see that it's not a real, you don't get much information from 7 points. And so if I can borrow a sentence from Maxime Descoteaux, give me this slide, we should say that we have to be careful, because 7 or 11 is not a good approximation of infinity. So sometimes when you do, so you have to be careful while you're actually pulling out of this propagator. So there are other methods, like for example, cubal imaging is kind of a simplification of kind of to get an approximation of the ODF we obtain with the SI, and in fact is using only a HARDI acquisition and using a Funk-Radan transform. I don't want to go too much in detail, but essentially if you want to know the probability of the spin displacement in this direction, you just need to integrate on the equator. This is a very simplified description cubal. There's more about that, but we can also do some kind of analytical cubal imaging. You can also improve the reconstruction, and also, if you want, again, from Maxime, we can actually improve the sharpness of this ODF by simply deconvolving using a model of ODF and get a sharper profile. But this is essentially the beginning of spherical deconvolution, because essentially we are deconvolving the diffusion ODF in order to get a fiber ODF. But the thing is, we don't need, in principle, to pass through diffusion ODF if you can go directly, spherical deconvolution directly on the signal. And that's the next slide. Okay, and that's the next slide. So spherical deconvolution. The spherical deconvolution, in fact, the idea is very simple. And it's based on the assumption, as I was saying before, that different fiber can be modeled by the same signal profile. So if this hypothesis is true, so if we can somehow assume that hard donuts is more or less good for all the fiber of the brain, and we can use this kind of information here. So we can also assume we have a fiber response. So if we know exactly the signal is coming from a fiber, then we can see the signal, the overall signal, just as a sum of different fibers, but also as a convolution of a fiber response model and a fiber ODF. Now, what we want to do in practice is do the opposite operation. So given the signal S, and so we measure this from the scanner, we take this, we can sample this from the data, or we can actually assume from a model of choice. And what we want, we want to recover this FODF. So the convolution is nothing else. We deconvolve the FODF starting from the signal given in a specific fiber model. Now, as you can see from this slide, there have been many methods for spherical deconvolution. And the reason for this is because at the beginning, things were not very nice. At the beginning, there was a kind of a problem about stability of the result. In fact, the convolution is clearly yield condition, yield pose problem. And if you don't do any specific regularization, if you don't do anything smart for that, you have a lot of instability. So a little bit of variation due to noise can give you completely different results. So at the beginning, there was kind of a problem about stability and regularization. So, and then we start this kind of a very short story of what's happened during the years, in the first, I would say, 5 years of of history of the spherical deconvolution. So we regularize a lot the solution, but at the same time we lose the improvement of angular resolution. So we end up to have FODF that looks like more diffusion on the F. So it was not good again. But then we work a little bit harder and we managed to get a good angular resolution at the same time good stability in terms of fiber orientation and noise stability. So now, very briefly, I'm going to show two examples of spherical deconvolution algorithm. Okay, so this is a constrained spherical deconvolution. It's probably the most known spherical deconvolution approach. And the idea, as you can see, is quite straightforward. So when we try to minimize the signal, so you try to regularize the solution, taking into account the non-negative information. So you know that your FODF, your lobe, should not be negative. So by just doing that, you can improve a lot compared to the unconstrained spherical deconvolution, and the solution gets more and more stable. However, there is something we need to take into account here. When you do CSD, you're still so you're more stable to noise, but you're still very sensitive to error in the fiber response. And in fact, because the method is always trying to fit fibers, and so to put signal, if, for example, if the model is different from the actual signal measure. But we can improve that, and recently a paper from Chantal Tax was actually able to propose a iterative calibration technique to improve the estimate of the fiber model, so improve the result of CSD. Now, there is another method, that's the method we developed in our lab, and is based on the Richard-Solution algorithm. The idea for this algorithm came from because we know that Richard-Solution was robust to noise, and also particularly flexible to different errors, and when also the point spread function, the fiber response function, was not well defined. So in our case, because we don't know exactly which one is the fiber response, we want a method that is robust also for this information. At the same time, was intrinsically no negative constraint, so we don't have to put any no negative constraint to enforce this. And now, in fact, if we look at the diffusion problem, we can see, of course, our data is very noisy, as we see in the previous talk. We don't know if there is any, or there is one or many fiber response we can use. And of course, we want the fiber orientation that are positive. So how it works? Well, through iteration, actually, we start from a first, this kind of a starting condition is actually all the directions are equal probable, and then through iteration we improve the estimate, and you can see after a few iterations we converge to a nice solution. Now, what is nice of this algorithm is that, first of all, it's not using spherical harmonics, so we don't have any truncation artifact or Gibbs ringing problem due to the convolution process, and also it has global convergence, so it's quite nice. And because also the semi-convergent property, we can also use the iteration as actually a nice and flexible regularization algorithm. So it's quite flexible, it's quite nice to use this. We further improved this algorithm recently to make also robust to partial volume effect, because one emerging thing is we observe is that it's not only a problem of resolving crossing, it's also you need to want the right fiber orientation when you want to do tractography. And we see, for example, when we have partial volume with gray matter or other tissue, this method, the non-negative constraint of all the method usually tends to switch off. And you can see here, so this is the first version, you can start to see false peak here, simply because we have 50% of gray matter. Now, if with the new version, we actually manage to regularize a bit more and dump small component, just with a specific regularization. So this is the simulation, and this is in vivo data. So now you can see that as soon as you get closer to the gray matter or CSF, a lot of spurious spikes disappear, while at the same time the fiber orientation remains constant. And but this one advantage I was saying before is not only to be stable to partial volume effect with tissue, but also we need to be stable error in the fiber response. In fact, there was a recent study comparing CSD with Richard-Solution, and you can see that when there is an error between the model and the signal, CSD tends to generate a spurious fiber orientation along specific direction. This could be a kind of tricky, for example, when I would say this is not an issue in healthy or more or less normal data, but when you have a pathological tissue, you might start to generate wrong fiber orientation in the wrong direction, so you have to be careful. On the contrary, Richard-Solution is free from this issue. However, it's not perfect. As you can see here, we have to pay a price. So the price is, while CSD tend to generate more false orientation to kind of fill the gap because of the mismatch between the signal and the model. Richer solution actually give you a more kind of blur FODF, so it kind of reduce in terms of angular accuracy, angular resolution. So it's kind of a trade-off. If there is not much anisotropy, richer solution is not going to give you any, it's not pushing too much, it's not too rich. So it's kind of a more conservative solution. And why it is important? It is important because now we can solve the crossing, we can see many directions, but we can also get that. So this is a nice picture, this is a nice example of tractographer, but if I tell you that this is the cortical spinal tract and this is the gene of the corpus callosum, you probably start to laugh, right? And this is, in fact, this is bad environment tractography. This is done specifically using very low threshold and using no specific constraint, pushing my algorithm only to get even random fiber presentation. And why? Because one thing is we need to learn that now with these new methods we are going to have more problems. In fact, because now we can choose between multiple directions each function. Now we have more chance to get it wrong. So we need to be careful when we use this advanced model not to generate too many. The fact that we see more crossing, it doesn't mean it's better. It could be even worse because you can get results like that. So you have to be very careful, in particular when you use kind of this connectomic approach, when you trust the result of tractography, we can actually go and look at the underlying anatomy of each connection. And this is actually, to link also with Carla and Alex's talk, is the future. Now the future is coming very quickly, I would say. And now with the multiband, we are probably soon abandon the single shell technique, the traditional HARDI technique. We probably are going to move quickly to multi-shell acquisition. So we are going to have soon multiple B-value acquisition. And in the case of multiple value acquisition, we can do nice things. For example, we can parcel it or can actually separate the different tissue compartment. And for example, now we can be smart enough to not resolve crossing fiber anymore in the CSF, for example. This is kind of the improvement that we still, well, the algorithms we are using actually are made to find crossing everywhere. And if we don't tell them, don't look here, they try to anyway to find something. But also it would be nice when we apply this technique, for example, in the boundaries between gray matter and white matter. Now we can better control for partial volume effects, so we now to see much better contrast or orientation and less false orientation. So in the future, I think probably everyone is going to move this, but I don't know if you already have multi-shell data. The Human Connect project has this data set, but if you don't have, you can still use richer solution, for example, it's fine. Okay, so just to summarize this part, this is what we have with DTI. You can see this kind of smarty field, this candy factory from Alex Lima industry. And then here on the right, we can see what we can do now with the spherical deconvolution. Now, as you see here, is 60 direction, cardiac gated, and B59. This is essentially is a DTI acquisition, a little bit kind of improved DTI acquisition, but it's not much different from standard DTI. And we can do a lot more, or we can do a lot better just using spherical deconvolution. And if we do that, it's not only for this, because immediately this is the tractography you can get. So if this was the problem we were seeing before, because we're not able to cross now with spherical deconvolution or any method that is able to resolve the crossing, we can now see this track and more. I just put an example here because I think Tim later will show more example of tracks. Now, one important point I want to make is about the different techniques. Where sometimes people came to me and say, oh, well, I'm using an advanced technique, I'm solving the crossing, that's fine, so any method is the same. Well, actually, you have to be careful because it depends what you want to do. For example, here we can see what they call a diffusion or the FODF spectrum, because we can go easily from a very blurred profile to a quite sharp profile here. And actually, there is no actually a discontinuity. It's kind of a continuum spectrum, depending how much regularization you apply in your method, how much sharpening. You can go from spherical deconvolution method very blur, or you can also use very sharp peak with DSI, depending what you do with it. So, but just to separate the two examples, just to keep the extreme. So on one side we have, for example, a completely unprocessed, unsharpened DSI. On the other side we can say this is what we can get today with standard spherical deconvolution. And just to give you an example how a different method can give you different result, I want to actually mention a recent debate that was on a couple of years ago about the Van Vedin theory about the grid. So because it was using DSI, and essentially is using kind of, let me see if I can go back, profile essentially where crossing is mostly resolved between 70, 80 degrees and more. he was actually reporting that he was able to see this kind of grid structure. In the original publication, he was stressing that the crossing were 90 degrees. Now, in the ongoing debate, things are a little bit changed. Now he's claiming that it's not nice only 90-degree crossing, it's more about this kind of grid organization. But importantly, he's also suggesting that because of this kind of structure, the axon in the coronary data, for example, are organized in this way. And to support this, he reported this kind of Crick paper, Crick reference from a book in 1954, suggesting actually you can see axonal degeneration doing this kind of sharp turn, sharp change of direction. In his kind of discussion, he criticized our reconstruction, saying actually this is not real. There are no fiber merging like that. And or even there are no, also at some point also said there are no things like U-shaped fiber. But is okay, we might be wrong, but it's quite interesting to notice that if this is Krieg and this is page 119, if we just turn 4 pages before on the same citation, we can actually see the same structure with axonal degeneration. So it's interesting to observe how this is a very interesting theory. It is a very interesting, interesting and also provocative theory about human anatomy. But it's interesting also how different methods can actually drive to complete different results. So be careful when you use your advanced method. So this is kind of a take-home message, okay? So remember that you're looking the world with different glasses every time you use a different methods. Now, just to conclude my talk, I want to go a little bit beyond crossing fiber, and because crossing fiber is not the only thing we can do with spherical convolution and other technique. And the fact is, since the first paper with spherical deconvolution in 2010, we started to work on what can we do with spherical deconvolution. We can only extract tractography and that's it, or can we get some kind of new matrix? And the idea is that in principle, because we are resolving different fiber orientation, we should be able also to extract track-specific information, not anymore voxel-specific information, because FA, mean diffusivity, is all about a voxel, not about a track. Now, if you look at, for example, if you try to simulate a signal from spherical deconvolution, you will see that, and you try to introduce some kind of degeneration in one of the fiber, losing volume fraction or radial diffusivity, whatever, you will see that one fiber probably is going to decrease or until it disappears, while the other fiber actually remain unchanged. So that's quite an interesting thing, because now we can have a tool that can actually follow the degeneration of the specific track, while the other healthy track remain the same. Now, if we do the same simulation with DTI, what we see essentially is the tensor just rotate a little bit, and the phase might actually change, sometimes decrease, sometimes increase, depending actually of the angle of crossing. So sometimes you see increase on a phase when you have a fiber is degenerating, and actually this kind of can be misleading. So you need to think twice when you interpret FA changes in degeneration. So we come out with these kind of indices we call orientation, intermodulation orientation isotropy. Raphael called apparent fiber density. Now there is recently another AFD called angular fiber density. So it's a bit of a mess at the moment in terms of terminology, but we are working on it, don't worry. But the concept is always the same. We are looking at the amplitude of the FOD, amplitude or integral of the lobe of the FODF. So how it works? Well, it is very simple. If you look at this at the arc with fasciculus, you can see that the amplitude of the absolute amplitude of FOD is not always the same in all voxels. So there is some more information that we can actually extract. If we look at the absolute amplitude of the FODF, we can actually follow some kind of continuity across the fiber. And in particular, if we select, for example, here, 3 voxels with the same FA, we can see this amplitude, the microstructure, the structure organization of the fiber is completely different in the 3 voxels. So we have more information we can pull out using this method. And for example, is just to conclude, you can see here that in the region of cross is the arc with fasciculus crossing with the corpus callosum. We have a region, this is the same region I showed you at the beginning with low FA. We see FA is going down on both fibers. But now if you look at this new index, we can see the crossing is actually made of a very anisotropic fiber, the arc with fasciculus, crossing with the less anisotropic fiber, the fanning of the callosal fiber. So that makes sense. And now this is the same with the corticospinal tract and the arc with fasciculus. Now, why it is important? Because think about mapping degeneration of fiber crossing with healthy fiber. So now, for example, we can see change that are really specific of the track, not just specific of a brain region. So I think that is a new way of looking at track information and tractography data in general. So I think I will conclude with a few take-home message. So the first one is clearly, yeah, the brain is a complex thing, and there are many crossings, so you have to think about that. So we need to use advanced methods, not just DTI might be not enough to map everything. We can now resolve the crossing. I think crossing probably is pretty much solved, but there are other problems we still need to figure out. For example, bending, kissing, fanning are still things that need to be included in tractography algorithm in a much smart way, I would say, and we need to take things into account. Also, although they are very similar, FODF and DODF, they have a different meaning and they're coming from different processing. And I will say my opinion is that for tractography application, you should go for FODF because it's sharper and require much lower b-value to get the same result. Yeah, fiber orientation need to be accurate because it's very easy to get it wrong. So I think in the future, it's not only who see more crossing is the best method. In the future, who see that the most right number of crossing is probably going to be the right method to use. So be careful when you use advanced method not to see this. If the fact you see new connection, new track, think twice before say, oh, I discovered a new track, because that can be coming from this. Now, just to conclude, and not this, going back again to the previous talk, it's not about only the model, because you can get great tractography reconstruction. For example, here is a Singulum done with DTI almost 10 years ago from Marco Catani. We spent a lot of time dissecting the data quality was optimized from Derek Jones, so it was an excellent data set. And now there are other papers coming out, not because they're using the wrong model, but simply because, for example, to compromise, for example, DSI to have a b-value of 8,000, you are limited to a voxel size of 3 millimeter or 4 millimeter. So at the end, even if you use an advanced method and you don't have the resolution, you might get much worse reconstruction. For example, you can lose completely the posterior part of the single. So think about the trade-off between methods, data quality, SNR, resolution, and of course, scanning time, because you just want to collect the data in 20, 30 minutes, but you don't want to scan for 1 hour and a half, definitely. So, and the last thing is this. Spatial resolution is one of the most important challenge we are fighting now in diffusion imaging. We want to go in higher resolution. And thinking about, for example, connectomic analysis, I want to just give you a kind of a scary example. Now, look at this picture. You see all the fiber converging at the center of the corpus callosum. And with the resolution we have today, 2 millimeter, 2 millimeter and a half, most of the time, the body of the corpus callosum is just 1 or 2 voxel thick, okay? So how can we expect to be able to discriminate between homotopic, heterotopic connection? How can we claim that we can actually do a connectome of interhemispheric connection? I think it's not possible. I think you have to be careful when you interpret your data from connectomics, because every time you pass through a single voxel, this is kind of a Big Bang paradox. Everything merges in a single voxel and then remerge on the other side, but you have no idea what's happened before. So careful when you interpret your connectomic data. Thank you.
Any questions? Yes?
Sorry. Good morning. I'm sorry, I have 2 questions. The first is, given the risk of false positives in tractography, can you comment on deterministic versus probabilistic models when you're using HARDI-based approaches? And my second question is, given the advantages of HARDI, without that much longer acquisition time, is there ever a scenario where DTI could be the better solution?
You mean DTI or DSI?
DTI. Given HARDI has so many more advantages, do you think there's going to be a shift away from DTI, or are there scenarios where DTI could actually still be a better solution?
Okay, so 2 questions. Let me start from the first one. I probably already forgot. And sorry, which one was the first one?
Sorry, the first one was, given the risk of false positives.
Yeah, probabilistic, deterministic. Yeah. Okay, probably I'm not the right speaker to answer that, because there will be a talk specific on tractography, but I can give you my opinion. I mean, if the data is good, and if you have a very high SNR, almost infinite SNR, probabilistic and deterministic should converge to the same result. So that's the main thing. The point is, with deterministic, we just track the most likely trajectory, and most of the time we just stop because the data is not good enough, the model is not good enough. With probabilistic, we have to be careful how we interpret the result, because probabilistic is mainly mapping the uncertainty of your data. So even people say, oh, I use probabilistic because I see more. It is true, but it's also true that actually we're looking, it's not an anatomical probability, it's a kind of a map of uncertainty. How reproducible is your data? So it's kind of the standard deviation of your track. So you have to be careful how you associate the term probabilistic in your anatomical reconstruction. So it's good. We are also moving from deterministic to use some bootstrapping and probabilistic, but probabilistic is mainly a mapping the uncertainty in your data. So just to give you a kind of another scary example, if you want to see more track, you just need to get noisier data. So that's kind of scary, okay? Now, for the other question was about DTI is going to die, essentially. I don't think so. I think that this is the best moment, probably, still to use DTI, because now we know exactly what are all the limitations. So if you know what are the limitations of DTI, you can use and you sure you're not making a mistake. So even, and that's what kind of a suggestion to make also to reviewers here in the audience is, sometimes we don't have to be bashing DTI because, oh, it's old, it's dead. We have to be kind of understand that if the method is reasonable, the results are kind of pushing out are okay, that's nothing wrong with DTI. Also, just to give an example, there are now hundreds of publications of the aquafasciculus using DTI. There is a huge literature, and though we know exactly what's going on, there is a huge correlation with clinical information. So for clinical purpose, I will not say throw it away. Now it's time to start to build up a new amount of publication using spherical convolution, use advanced method, and see if they go together. One thing we have seen, for example, with spherical convolution, the aquafasciculus now is huge, it's much bigger, and probably some components are not related with language. So if you try to do a correlation, you might get a lower correlation score because you're actually pulling in other information from other track and not necessarily related. So it's kind of I quite like this challenge because we are starting to see new things. So don't forget DTI now, still using, but keep an eye open for the new methods. Oh, I'm working, so if I have to choose, I'm going for HARDI. Definitely, I'm going to set up a acquisition at least 60 direction, be 1500, 3000. So I'll try to optimize in a way that can be an investment for the future. So if you start now a study, don't start with 6 direction, 10 direction, and be 1,800 because actually it's like shooting in your foot. You want to be kind of ready for the next step. So if you're collecting now high quality data, you might want to analyze first quickly with DTI to see how it goes, but then you already have the data ready for do more. I think, by the way, there is not need actually to wait for that. You can already analyze it directly with spherical convolution, and it's fine.
Okay, then one final quick question.
I just wondered what you thought about using CSD with a smaller number of directions than is typically used, like say 30 directions. If you look at the results and they look reasonable, is there any other way to sort of validate what you have? Okay, I'm not using CSD because of kind of conflict of interest. I'm using Richardson-Lucy, but I would say that for Richardson-Lucy it's fine. I mean, we managed to resolve some crossing at B1000 and 30 direction, 28 direction, fine. So it's not great. I mean, you're able to see much less crossing, of course, because it's not the optimal. I mean, see, the optimal will be something like 60 and more, and B value 3000. There's a publication from Donald Tournier that actually suggests that it's kind of a gold standard you want to achieve to get the best possible crossing. You can decrease this data set and you start losing little by little the ability to cross. We even tried to do crossing B value 820 direction. We managed to see very few crossing, but some crossing were still there. In terms of CSD, I think it's more or less the same thing. You can push it a little bit more, but I think one of the issues is if you go too much low B value and not enough information, you might risk to start to generate a lot of false orientation, but I might be wrong here, I'm not sure. So you can try, but careful. You should basically try to drive a Formula 1 car off-road. So it might work, might not.
In a way, it's like the law of preservation of misery. right? If you want more information, you need to acquire more data. That's how it goes.